this chapter, we will be looking at various types of functions. In this lesson, we will be talking about the factor theorem.
Okay, so for the next couple of moments here, we just want to take some time here and talk about some relationships in the data here, relationships in the concepts and the vocabulary here. So we're going to start with something that looks like this. Let's say we've got x squared minus x minus 6 is equal to y. Okay, now that's a function. Okay, here we'll zoom in just a little bit here. Whoops, wrong way. Okay, so this is our function here, function of x. So it demonstrates a relationship between y and x. Okay, if you were to plot the points here, okay, you would say x and y, but you can do better than that, right? You can say x and then y is the same as x squared minus x minus 6. And I like writing it like this because we know that y is a dependent variable and x is the independent variable. But when you write it like this, you show exactly how y depends on x. Y is the x coordinate squared minus the x coordinate minus 6. There you go. Now, when you plot these points, you're going to get that parabola. Okay? Great. There you go. Now, if you allow y to go to 0, then what you're doing here is you're setting yourself up to look for what we call the zeros of the function. Okay? The place where the function goes to 0. Now, when we talk about the zeros of the function, we're referring to the y coordinate going to 0, not the x coordinate going to 0. I have control over the values of the x coordinate, the independent variable. That's my part. If you want to think of it in the sense of an experiment, it's the manipulated variable. I manipulate the variable. I know when x goes to 0. What I'm curious about is what happens to gets y to go to 0. So when I let y go to 0, I'm looking for the zeros of the function. Okay? But when I do that, a couple other things pop up here. First of all, if y goes to 0, okay, well, think about the parabola that we just sketched here. When y goes to 0, that's a point along the x-axis. Okay, remember that any point on the x-axis here has got a y-coordinate of 0. So here are my two x-intercepts. So the zeros of the function actually are graphically, okay, the x-intercepts of that graph here. Now, additionally, when you set y equal to 0, we create an equation. Now, this is a function here. It's a relationship between x and y. As soon as you drop that second variable, there's no relationship now between the independent variable and the dependent variable. This is just an equation. And we're going to start to look for the roots. And we do that by factoring. Okay? Because when it's written in factored form here, I've got this term multiplied by this term here. If the result is equal to 0, that means one of these terms is going to be equal to 0. Now, it could be x minus 3 equals 0. So x minus 3 could equal 0. And if you bring that over, you get x equals 3. Now, granted, that doesn't make this one equal to 0. That makes this one equal to 5, but that's okay. 0 times 5 is still 0. Just like if you make x plus 2 equal to 0, that means x could be at negative 2. That doesn't make this equal to 0. That makes this equal to negative 5, but negative 5 times 0 is still 0. So these are the roots of the equation here. And so we want you to understand that the roots of the equation are the same thing. Okay, where the graph hits the x-axis here, the x-intercepts here, right here, this is where x equals negative 2. This is where x is equal to 3. Okay, those were the roots of the function. They are the x-intercepts of the graph, and they turn out to be the zeros of the function. Three different ways of looking at really the exact same thing.
Determine the remainder when the polynomial x cubed plus 2x squared minus 5x minus 6 is divided by x plus 1 using long division. Then factor the quotient and rewrite the polynomial as a product of those factors.
Okay, so this one wants us to do long division. Here we go. So we'll plug in x plus 1 here, and then we've got the dividend here will be x cubed plus 2x squared minus 5x minus 6. Okay, so I need to multiply x by x squared to get that x cubed to pop out when I multiply it through. And then the x squared gets multiplied by both those terms. So this becomes x squared. And you subtract. And so that first term, that term with the highest degree, goes away. Then 2x squared minus x squared is just x squared. And then we bring down the remaining pieces and start again. We're trying to get rid of the x squared here. So I'm going to plug, what am I going to do? I'm going to put just an x up here plus x. Multiply that through, we'll get x squared whoops, plus x, don't know why I wanted to write 1 there, but x squared times, x times x squared. I keep saying that. I'm anticipating the answer. X times x is x squared. X times 1 is x. There we go. Subtract, and we're going to get the x squareds will disappear, then negative 5 minus x will be negative 6x, bring down the negative 6. And actually, if I plug negative 6 into here, you're going to see this happen right here. Okay, now I didn't give myself a heck of a lot of room there, but the answer is the remainder is going to be 0. That worked out beautifully. Okay, so the remainder was 0 when I divided by that x plus 1. Now this next part of the question says, now factor the quotient and rewrite the polynomial as a product of these factors. Okay, well the quotient that I got, okay, was x squared plus x minus 6. And so if I factor that, I'm going to get x plus 3, x minus 2. Okay, so now this means p of x is equal to, if you write it out, if you write it out the way we were looking at before, one of those division statements here, think about what's going on here. I would multiply my divisor. P of x would be the same as my divisor times my quotient, but now I factored the quotient, so I can write it out like this. It's the same thing, it's just in factored form. And I would add the remainder, but the remainder was 0. So this is what the divisor looks like. Sorry, divisor. The dividend looked like. This is the same as the original polynomial. Now, evaluate the polynomial at these 3 values here. Well, if you evaluate p at negative 1, okay, negative 1 cubed is going to be negative 1 plus, well, negative 1 squared is going to be 1 times 2 is 2 plus 5. Okay, so this is going to be, that's going to be positive 7. Put those together, minus 7. That's going to go to 0. Isn't that interesting? Isn't that interesting? You know, because over here, I know what this is equal to. If I plug negative 1 into this, it doesn't even matter what happens here. This is going to force the whole thing to go to 0. Interesting. P at 2. Okay, if I plug p at 2 into this, 2 cubed is going to be 8. And this is going to end up being 8 as well. So that's going to be 16. So minus 5 times 2 is going to be negative 10. Minus 6, negative 16. Well, look at that. That goes to 0. Huh. Interesting, because over here, if I plug 2 into this term goes to 0. This factor, I should say, goes to 0. And the whole thing goes to 0. Huh. It's almost like these two are identical. Let's take a look right now at negative 3. If you plug negative 3 in. Let's go up here, negative 3. Negative 3 cubed is going to be negative 27. 9 times 2 is going to be 18. This is going to be plus 15 minus 6. Okay. So 18, 15 is going to be 33. Negative 27, negative 6, negative 33 goes to 0. Isn't that interesting? So what do I notice here? Well, I notice that if x minus a is a factor of p of x, okay, if x minus a is a factor of p of x, then p of a is equal to 0. Now that's no big surprise to us, because if something is a factor, then the remainder is 0. And this is really just an application of the remainder theorem that we looked at the other day. Okay. Now, there it is. That's just a very, very specific application of the remainder theorem, but it helps us find factors. So if I know, for example, that p of a is equal to 0, then I know that x minus a is a factor.
Here is a more formal statement of the factor theorem.
So this takes us to the more formally stated factor theorem. The factor theorem states that x minus a is a factor of the polynomial p of x if and only if. Now this is what I was trying to get at before, if and only if. So it doesn't really matter what direction you go, okay? If and only if p of a is equal to 0. So that means that if p of a is equal to 0, x minus a is a factor, and if x minus a is a factor, p of a is equal to 0. That's what the if and only if means. It goes both ways. Okay, and that's what this is trying to explain here. So, now what we're going to do is we're going to spend a little while here applying what we've just seen here in the factor theorem to answer some specific questions.
What is the corresponding binomial factor of a polynomial, p of x, given the following values of its 0?
Okay, so here we go. If p of 2 is equal to 0, then what that means is x, what should be happening here is x should be in the middle there, right? This should be p of x here, but this is now p of 2. So that means x is equal to 2. Bring that over. X minus 2 is equal to 0. There's my factor. Okay, so my factor that I'm looking for is this factor, x minus 2. That's a factor of the polynomial. Same thing for this one. X should be right there. So this is now letting me know that x is negative 4. It's been replaced with negative 4. Bring that over. I get x plus 4 is equal to 0. And that tells me that there it is. X plus 4, that's the factor that this is implying. Now I'm doing it like this. You probably, for these two questions, could have jumped to the answer very, very quickly without even thinking about it. This is the one that's going to throw people off a little bit. Okay, a lot of times people say, oh, look, this is just x minus 2/3. Yeah, no, that's not actually correct here. Okay, there's something going on here that hasn't quite been dealt with if you answer the question like that. The best way to look at this one is to state, okay, look, that should be 2/3. X should be it should be x right there. It's 2/3. So x is being replaced with 2/3. Now, bring the 3 up. Bring the 2 over. And now I've got that expression there equal to 0. Now my factor is 3x minus 2. That's the factor that we're looking for. Okay, and the reason why this happens like this is normally if you had something like this and you were looking for the x-intercept, what you would do is you would set 3x minus 2 equal to 0. You'd bring that 2 over, and then what you would do is you would divide. Okay, you divide by that 3. So x is equal to 2/3 here. If all you do is bring that 2/3 over, make this x equals 2/3, then bring the 2/3 over. Granted, you've addressed the addition here, what you did to move that negative 2, okay, what we see as a negative 2 here, to make it positive 2 on the other side here. But you never dealt with the division. Okay, there was some division here that made this 2/3. You've never balanced that out and gone backwards here by multiplying. If you state that this is the root here, or the factor, you have to deal with the division, okay, by multiplying, and then deal with the addition or the subtraction here by bringing that term over.
Which of the following binomials are factors of the polynomial x cubed plus 4x squared plus x minus 6?
So now this question asks us to go the other way. Now what we're going to do here is we're going to just suggest a binomial, and we're going to check to see if it's actually a factor. Okay, but we're not going to go through and do the division. Please don't go through and do the division here. Let's use the factor theorem. If I'm checking x minus 1, then what I want here is I want p of 1 to equal 0. I don't know if that's true, but that's what I want to be true here. So we're going to look at p at 1 here. If I plug 1 into this, I'm going to get 1 plus 4 plus 1 minus 6. So 1 plus 4 plus 1 minus 6. Okay, so that's 1 plus 4, 5. Oh, look at that, equals 0. Okay, whoops, and I should probably actually write this as p at 1 just to be really clear here. P at 1. So yes, it's a factor. Okay, good. Now, x minus 2. If I'm going to check x minus 2, then I want p of 2 to equal 0. Don't know if that's true, so let's just check here. P of 2. Okay, 2 cubed is going to be 8. 2 squared is 4 times 4 is 16. Plus 2 minus 6. You know what? I don't even really have to evaluate this to have a pretty good sense that this is not going to go to 0 here. I've got 8 and 16 and 2. That's going to be 26. Minus 6. See, that minus 6 just isn't big enough here to balance these things out here. But it's going to end up being 20. And so what this means here, this is not a factor. I'm not interested in the value here if it's not 0. Doesn't matter what it is. Okay? All I'm concerned about is whether the result is equal to 0, because that will tell me that this is a factor. So that's it. It doesn't matter whether this could be a million, could be negative 5, could be negative whatever. It doesn't matter. If it's not 0, don't care. So over here, what I'm looking for here is p at negative 3 to be 0. Don't know if that's true. Let's check it out. So negative 3 cubed is going to be negative 27. Negative 3 squared is going to be 9 times 4 is 36. Minus 3 minus 6. Okay, so what do we got here? Minus 27 minus 3 is going to be negative 30. Minus 6 is negative 36, and there it is. Plus 36 is 0. So yes, it's a factor. Because that's all I need. I just need that to go to 0. Perfect.
At this point, we're going to take some time to introduce the integral zero theorem.
Now we're going to look at this thing called the integral zero theorem. That sounds a lot more intimidating than it actually is. Basically, it says this. If a polynomial p of x has any factor of the form x minus k, then k is a factor of the constant term of the polynomial. Okay, so this means that the factors of the constant term are possible integral zeros that we will test. Now, to really understand what that last sentence is saying, you got to look at some examples. Watch me go through a couple of examples, then you'll see, oh, okay, I see where this is going here. But to start off with, we're going to assume right now, okay, that a polynomial can be factored kind of nicely here. And just to illustrate what's going on here, let's say you've got some p of x. Actually, we'll zoom in a bit here. Let's say we've got some p of x, and it can be written as x minus a, x minus b, x minus c, because this is the standard form, okay, of the factored form of a polynomial. Okay, now, granted, there might be some coefficients up front here as well. Yeah. But this is basically the standard way to write this. When you expand this out, okay, you kind of FOIL this all out here, multiply it all out here. Your first term is going to be the product. Okay, the first term is always the product of the first terms in all of these. So in this case here, I would get x cubed. Now, there are actually, interestingly enough, there are special rules that account for the product, okay, or the coefficient of x squared, of x. Okay, there are rules about the roots, the way these things get combined here. Now, you don't really need to know those right now. What I do need you to understand, though, is that there's some symmetry here. So just like the first term in this expansion is the product of the first terms of these factors, the last term, or the constant, is going to be the product of the last term in each of these factors here. So this last value is going to be ABC multiplied together. There will be no x in it, just the constants from each of those factors multiplied together. And that's what we're trying to get at here. Okay, in factored form. Okay, when it's in factored form, okay, you can see all of those, the factors quite clearly, all of those constant values in the binomials. When you expand that out, what you end up with is a polynomial in which the constant term, the final term, is the product of those numbers.
List the potential integral zeros of f of x equals x to the fourth plus 2x cubed minus 3x squared minus 8x minus 4 by following the following steps.
So now in this question, we have an opportunity to put to good use that integral zero theorem and the factor theorem, kind of everything that we've looked at before. It all kind of comes together here nicely. So list the potential integral zeros of this, okay, polynomial function here by following these steps. Okay, the first thing we're going to do here is look at the factors of the constant term. Okay, well, the constant term in this case is negative 4. Okay, now its factors are, okay, and actually maybe what we'll do is we'll zoom in a little bit here. For negative 4, its factors are, well, what are the factors of negative 4? Well, it could be plus or minus 1, could be plus or minus 2, and then plus or minus 4. Okay, I can by putting these guys together in different ways, I'm going to come up with negative 4. Those are my possibilities. Now, I'm not going to go crazy with this. Don't start thinking about 8.5 sort of thing. Like, well, I could multiply those together. The word integral here is implying integer. Okay, integer zeros. So I'm just looking for integer values here, no fractions, nothing like that. That's as far as I'm going to go here. So when it says the potential integral zeros, okay, well, that's what we're talking about here. Okay, the potential integral zeros of the function here will be x equals plus or minus 1, plus or minus 2, plus or minus 4. Now, actually, okay, what that suggests is that the factors here, the possible factors, okay, and I'll write it out like this. My possible factors are x plus 1, x minus 1, x plus 2, okay, x minus 2, x plus 4, x minus 4. Okay, those are the possible factors here. Now, in my next step here, it's asking for the actual zeros using the factor theorem. So what I'm going to do here to test these things, I'm going to start to evaluate. So I'm going to take my polynomial, which if you look at the top here has been labeled f. Okay, and I'm going to start to evaluate at these values. So I'll start at -1. Okay, and we go up here, f at -1. Well, this is going to end up being 1. Okay, and then this will end up being -2 because the negative will pop out. -3 plus 8 minus 4. Okay, well 1 plus 8 is 9. -2, -3, -4. Oh, look at that. That's 9 as well, but negative, so that's going to go to 0. So there we go. So what we know right now is that x equals -1 is a 0, okay, of this function here. Now let's try f of +1, because you never know. Could be. If we plug 1 into this, +1, now 1 is an easy one to work with. This is going to become 1 plus 2 minus 3 minus 8 minus 4. Okay, well, you know what? I don't even have to figure that out. This is 1 plus 3. Sorry, 1 plus 2 is 3 minus 3. Those are going to cancel, and then I'm going to be left with a big negative, -12 here. -12. So, not a factor. Now let's move on and try +2. Oh, sorry, let's do -2. We'll do the negatives first. Okay, -2. Come up here. -2 to the 4th is going to be +16. -2 cubed will be -8 times 2 is going to be -16. Oh, okay, I like that. Those cancel. This will be +4 times -3 will be -12. Minus, oh sorry, it was -2, so this is going to be +16 minus 4. Oh, and look at that. -12 and -4 is going to be -16 plus 16, 0. So there we go. So this is going to equal 0. So therefore, x could equal -2. And there's a possible, or there is a 0 for this function. Okay, so now let's take a look at what happens with 2, f of 2 here. Okay, so we'll go back up to our original function up here. We'll plug in 2. 2 to the 4th is going to be 16. 2 cubed is going to be 8 times 2 is going to be 16. Okay, well that's going to get bigger there. It's going to be 32. 2 squared is going to be 4. Times -3 will be -12. This is going to end up being -24. Sorry, 2. What am I doing? Sorry, I have no idea why I did that. It's 2 that I'm plugging in, not 3. So this will be -16, and this will be -4 here. Okay, but this actually works out pretty good here because we've got this 16 cancels with this one, and -12 and -4 is going to be -16 as well. So actually, this goes to 0 as well. And so I know that this is going to be a factor. Well, this is pretty good. This is pretty cool here. Now, I am running into kind of a weird situation right here where I can kind of tell that this is going to be, this is going to be the end of it. And the reason I say that is because I know that those numbers there are going to form my integral zeros, okay? And that the factors that are going to go along with this, okay, are going to be x plus 1, okay, x plus 2, x minus 2. Now, when I multiply those together, I'm going to get, if I multiply these values together, I'm going to get -4, which is the constant term right back there. So that is going to spit out a -4 here. So I can already anticipate that if I check the final two roots that I have here, they're not going to work here. Okay? But something is happening here. Something there's a missing term here because if I multiply this all out, I'm only going to get a cubic. So what I'm suspecting is that the way that this is working here is that I'm guessing, okay, at this point, this is just a guess. I need another factor in there, but when I multiply my constants out, they're already getting me -4. So I kind of just want another multiple of 1 in there. So I'm guessing that this is supposed to be x plus 1 times x plus 1. So that was squared, okay, times x plus 2, x minus 2. Now that's a fairly educated guess in this case here, and almost positive I'm correct here. But just to illustrate here, I'm going to go back up to part C, and I'm going to check the remaining two roots. Okay, I have checked plus minus 1, sorry, negative plus 1, negative plus 2, and now I'll check both of the 4s here. So negative 4, and actually in this case here, I'm going to do this on the calculator. So I'm going to plug in, there we go. So this will be negative 4 to the 4th plus 2 times negative 4 cubed minus 3 times negative 4 squared minus 8 times negative 4 minus 4. 108. Okay, well, equals 108. That is not a factor. Okay, and I kind of anticipated that. But now let's check positive 4 here. Go back up. Now, to do this, what I'm going to do here is I'm going to press second enter. And what that does is bring down the previous line that I just entered here. And I'm just going to go back here and delete those negative signs for the negative 4. Just delete, delete, delete. Press enter. Ooh, and I'm getting 300 this time. That really wasn't it. Okay, so 300. Whoops. Not factors here. Okay, not. There we go. And that is actually very consistent with what I thought it was supposed to be. Now, last question here. The graph of the function is going to have x-intercepts where? Well, based on the factors that I've been able to pull out of this, I can anticipate it's going to have x-intercepts at x equal to negative 1, negative 2, and positive 2. And actually, I can double check that. Okay, just by going to my calculator. I'm just going to graph it. I will graph that function. Okay, so it was x to the 4th plus 2x cubed minus 3x squared minus 8x minus 4. And I will just press my zoom number 6 to go to standard zoom settings. I'll just wait for it. And there we go. Notice that I've got x-intercepts there at negative 2, negative 1, and positive 2. Okay, just the 3. And we'll talk about why. There's other reasons why I anticipated that the x plus 1 was going to be squared, and we'll see other reasons here in a couple of lessons.
What are the zeros of the function f of x equals negative 2x times 2x minus 3 squared times x minus 5 times x plus 7?
All right, so to answer this question here, what are the zeros? What we're going to do here is we're going to identify every factor in this expression. So, and every factor has the possibility of going to 0. So when I read this thing through here, I've got a factor of, what is this? I've got my coefficient over here, negative 2. Well, does negative 2 equal 0? No, negative 2 doesn't equal 0. That's a kind of a goofy thing to ask here. Of course it doesn't equal 0. There's no variable there. There's no way it could equal 0. Oh, okay, so that's not it. The next factor here is x. Does x equal 0? Well, yeah, it is possible for x equal to 0. So one of my possible zeros here is going to be x just equaling 0. Okay, could go through the origin. The other factor that I've got here is 2x minus 3. Now it's being squared, but that's not relevant here. I'm just interested in what the factor is, whether that factor is going to 0. Because if it does, squaring it will just reinforce that. Okay, 0 times 0 is 0. Now bring the 3 over, so 2x is equal to 3. And then divide by 2, and x is equal to 3 halves. So 3 halves is a possible 0. Okay, and so that could work. Okay, the next factor that I see is this x minus 5. Could x minus 5 equal 0? Yep, as long as x was equal to 5. There we go, that works. And finally, I've got x plus 7 equal to 0. And could that be equal to 0? Yep, as long as x is equal to negative 7. So there we go. So our possible zeros here are going to be 0, 3 halves, 5, and negative 7. Now, again, it might have looked kind of goofy the way I started this one here, looking at negative 2, but I don't want you getting confused by this. A lot of times people will just throw down the number negative 2 because they see it there. Before you can identify what the zeros are, you really need to see this thing in factored form, and what we're looking for are the variables, the factors with the variables in it. you're probably far better off seeing this as negative 2 times x. So negative 2 is a factor, x is a factor, treating them separately and realizing that this constant here could not equal 0, so it's not even an issue here, and just ignoring it.
What are the possible integral zeros of each of the following polynomials?
Okay, so what are the possible integral zeros? Here we go. So remember what we've said here. The real focal point of our investigation here is that constant. Really what we're looking for are factors of that constant right there. And so x, okay, the integral zero here, okay, and again, remember, we're looking for integer values here. Possible factors of negative 16, well, that could include positive 1, could include negative 1, could be positive 2, could be negative 2, could be positive 4, could be negative, whoops, I don't know why I want to put 6 there, that was weird. Negative 4, okay, could be positive 8, could be negative 8, okay, could be positive 16, could be negative 16. Now there's a bunch there. Okay, those are all possibilities. Now for the next question, we're looking at 12 here. We're looking at factors of 12. Now, it could be positive 1, could be negative 1. Now, someone's going to say, well, wait a minute. No, it really couldn't be negative 1 because there's no negative showing up in here. I really wouldn't expect it to do. And you know what? You're probably right here, but that's not what they're going to be looking for when they ask a question like this. Sorry, I'm just going to expand that out a little bit. Okay, it could be positive 1, could be negative 1. Okay, they're going to argue, for example, well, negative times a negative is a positive, so maybe we've got even groupings of the negative signs here. Okay, regardless, what you really want to do here is just to kind of ignore everything else here. We're just going to look at factors of 12, and in this case, negative 1 is a possible factor, okay, because it could be like negative 1 times negative 12, giving you positive 12. This could be positive 2, could be negative 2, positive 3, could be negative 3, positive 4 could be negative 4, positive 6 could be negative 6, positive 12 could be negative 12. 12 has a whole bunch, okay? And so these are the possibilities that you would have to go through and test if you were going to try to factor this polynomial. And again, these are the ones that you'd want to test if you're trying to factor this polynomial right here. Now, however, just before we get on into that sort of work here, you can be clever with this. Let's say you go through and test, for example, positive 1 and negative 1, and neither one of those work to get you that 16 there. Well, then you know automatically that 16 and negative 16 won't work either. Because the only way like the 16 here will work would be if a positive 1 works or a negative 1 works, okay, or some combination there. So you can start to get kind of clever as you're testing those zeros there, and eliminate certain possibilities that just simply won't work. If one part of them doesn't work, then the other part can't possibly work. And we're going to see that sort of thinking here in just a little bit.
We're now going to take a couple of moments to outline a method of factoring that uses the integral zero theorem and the factor theorem.
Okay, so before we get into actually applying this or putting all these things together, let's just talk about really quickly what our plan of attack is when it comes to factoring a polynomial, okay? So if it's degree 3 or higher, this is what we're going to do. The first thing we're going to do is look for common factors, okay? Pull those all out because you want to get rid of those. If a common factor has been multiplied through, it's just mucking it up, okay? Making it harder to kind of clearly see what the factors are. And then check for grouping. Oh, please always do that first, okay? Now, you're not going to see that pop up often as a possibility, but when it is there, it is so much faster than what we're about to look at. Okay, because then your question will basically end there with grouping. But for the most part, that's not going to actually happen here. So this is what you do next year. If grouping doesn't work, okay, then what you do is you're going to look at your constant term and you're going to get your potential zeros out of that. So what we just did in the previous question, looking at those possible values, those possible integral factors of that constant. Then we're going to go through with the factor theorem and we're just going to start systematically checking them. And I know that's a little bit tedious here, but what you've done though is at this point here, we've taken, for example, a situation where you might look at a cubic polynomial. Prior to this moment, you'd look at it and go, I haven't got the foggiest idea what the possible roots are. And so we've reduced an infinite number of possibilities to just a small finite number. Okay, that's actually a huge step forward. Now granted, it's going to be a little bit tedious. It's going to feel a little bit tedious as you're going through this, but that's just a substantial step forward here. So as soon as we find that 1, 0, what we're going to do is we're going to use that 0 and we're going to perform synthetic division or long division if you want. Doesn't really matter. Synthetic is quicker though. And we're going to divide that out and be left with our quotient here. And then what we're going to do is we're going to factor that quotient because ultimately we're hoping that it's going to be, well, if this was a cubic, if this is a cubic, when you factor out that binomial, you'll be left with a quadratic, which should be easy to factor. If this is a quartic, once you've factored that out, you're going to be left with, very likely going to be left with a cubic. Then when it says factor the quotient, you're going to go right back to the beginning here and start again. Okay? And basically until you've broken that thing down into a quadratic, and then you just factor the quadratic like you've been doing for quite a long time now. And then you just list out all the possible factors, or sorry, possible factors. You list out the factors of the polynomial. This last step here, it seems kind of like a trivial little end to the problem. But what I've seen students do here is you go through all the work, identifying all of the different factors. All of them are there in your work. There's one up here, there's one here, then there's maybe two down here. And I've seen people just walk away from the problem and never actually put them together. This times this times this times this equals my polynomial, which is what you're being asked to do when you're being asked to factor a polynomial. Okay, so please don't leave the question undone with all of the pieces still there. Please make sure that you remember to write out all of the possible factors. I keep saying that, possible factors. To write out all of the factors that you found multiplied together to equal the polynomial.
Factor each of the following. 2x cubed plus 3x squared minus 3x minus 2.
So here we go. The first thing we want to do is look for any common factors, and there aren't any. The next thing that we would do here, maybe, and I'm going to do it like this because I have an idea where this is going here. First thing I'm going to do here is look for grouping. So I would group together the first two terms here. Okay. I'd put a big old plus sign in between, and then I'd group together the last two terms. Now I really do want to make sure that I put parentheses around that and pull that negative in, because if I was to just put brackets around that, and a lot of times people do this, they inadvertently factor out the negative when they don't actually mean to. Okay, by putting the brackets around. So if I think in my head, okay, put a plus sign in between, okay, put a summation in between and the parentheses there, then I'm not going to make that mistake here. Now, take out what's common out of those two terms. I'm going to take out the x squared, and I will be left with 2x plus 3. Here I will take out the negative, and I'm left with 3x plus 2. And this is where factoring by grouping stops, because this should be the same as this if factoring by grouping is going to work. So that's no good. So we're going to move on here, and what we're going to do is test our integral zeros here. So notice that factors of negative 2 here will be x equals plus or minus 1, plus or minus 2. Those are my options here. So let's do what I'm doing here. Let's check, first of all, x plus 1, which means we're going to check x equal to negative 1. We're going to check that inside there. So if I plug negative 1 into this, this is going to end up being negative 2, okay, plus 3. If I plug the negative 1 into that, that's going to be plus 3 minus 2. Okay, well this is going to be negative 4 plus 6, so this is going to end up being 2. So not a factor. So we check the next one. X minus 1 means I'm going to plug in positive 1 into there, so p at positive 1. Okay, if I do that, that's going to get me 2 plus 3 minus 2. Okay, there it is. There's my 0. So I know that x minus 1 is a factor of that polynomial. So now I'm going to do synthetic division. Okay, I'm going to put the 1 out front here, because I just like doing synthetic division that way. My coefficients will be 2, 3, negative 2. Now I already know that this should be a factor. My remainder here should be 0. Okay, So this is another way I can kind of double check that I'm on the right track. If my remainder ends up being 0, I know I've done this correctly here. So bring down the 2, okay, then multiply 1 times 2 is 2, and add. So 5. 1 times 5 is 5, add. 1 times 2 is 2, add, and I do in fact get 0. So now, thus far, I can tell you that my polynomial has got to be my divisor, which is going to be x minus 1 here, times, well, this is my remainder here, so this is going to be 2, 5x, 2x squared. So 2x squared plus 5x plus 2. And because this is just a nice, straightforward quadratic, I can guess pretty quickly at what the factors are. This is 2x squared, so it's going to be 2x and x. If I put a 2 there, I'm going to get a 4. Just have this plus 1. And there's my 5x. Okay, when I go 2x times 2 is the 4x, 1 times x is x. Together that's the 5x. That's what I'm looking for here. So that is my polynomial in factored form. Good.
X cubed minus x squared minus 8x plus 12.
All right, so once again, first thing I'm going to look for here, is there any common factors? And to answer that question, I say no. No, there's nothing common to all of those. The next thing I'm going to look for here is factoring by grouping. So I will put parentheses around the first two terms, big old addition, and then pull the negative in, negative x plus 12. Okay. Again, because I want whatever sign that is to be associated with that term there. I don't want to inadvertently factor out a negative without actually doing it. Okay, so we leave it like that, big plus sign in between. Take out what's common out of those first two terms. Take out the x squared, and I'm left with what is that? X minus 1. Take out what's common here. Looks like I can take out a negative 4 there, and that'll get me positive 2x minus 3. Yeah, you know, I don't see anything common there to pull out, so that's probably not it. Okay, now we're going to apply the integral zero theorem, and I'm going to look at the 12 there, and oh boy. Well, okay, could be factors of 12 here. Okay, could be, and I'll zoom in on this right now. Factors of 12 here, this could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Yeah, that's awesome. Lots of good options there. Okay, now we'll zoom out. So now I'm going to start to check these. I'll check, for example, x plus 1 to start off with, meaning I'm going to plug in x equals negative 1. So p at negative 1, well, if I plug that in here, okay, negative 1 cubed is going to be negative 1. Negative 1 squared is going to be positive, but there's a negative out front there, so negative. If I plug a negative into that, I'm going to get positive 8. Okay, plus 12. Well, 8 and 12 is 20. Minus 2, this is going to be 18. Well, that's not 0, obviously, so that's not a factor. So then I'm going to test x minus 1. So x will equal positive 1. So p at 1. And this is going to get me, well, that's going to be 1 minus 1 minus 8 plus 12. Okay, what do we got here? That's going to be 1, those are going to disappear. Negative 8 plus 12 is going to be positive 4. So that's not a factor. Okay? Well, I keep looking here. I keep looking. So I'm going to test x plus 2, which means I'm going to let x equal negative 2. So p at negative 2. We'll check this out. Whoops. Okay. Negative 2 cubed is going to be negative 8. Negative 2 squared is going to be positive 4, but there's negative out front there, so negative 4. Negative 8 times negative 2 is going to be positive 16 plus 12. Okay, well, negative 8, negative 4 will be negative 12, and the 12, those will cancel, so I'm left with 16, so that's not it. So x, I'm going to check x minus 2 by plugging in x equals positive 2, so p of 2. Okay, we'll try this again here. 2 cubed is 8, 2 squared is 4, so 8 minus 4, minus 16 plus 12. So what have we got here? Negative 22. Oh, there it is. There it is. Now I took you on a little bit of a ride there, but there is another way that we could have figured that out really quickly here. Okay, go to my calculator. Okay, and actually I'm gonna do it like this because I don't want that glare to keep popping up there. Okay, so I'm gonna go to y equals, and I will enter in, and what did I have there? It was x cubed minus x squared. Now what was that? Minus 8x plus 12. Now, what I'll do here from here is go second graph to get into my table. And now, what I'm going to do here is just look for where that thing goes to 0. And notice, it goes to 0 when x is equal to 2. Sorry, when x is equal to 2. So I can see that right off here. I'm looking for the x-intercepts. I'm just going to look for where the y-coordinates equal to 0. I could have guessed that right away. Now, I didn't, because I want you to know that the procedure here is what we're doing. But yeah, I could have gone to the calculator right away and known that that was the issue. Now, I'm going to divide by this by putting, by using synthetic division. I'll put the 2 out front there. I'll list my coefficients. So 1, minus 1, negative 8, and 12. And I already know that this remainder here should be 0. Should be 0 there. Let's follow it. Put the 1 down. 2 times 1 is 2. Add, and I get 1. 2 times 1 is 2. Add, and I'll get negative 6. 2 times negative 6 is negative 12. Add, and I do in fact get 0. Excellent. So now I'm going to write my division statement here. P of x is going to equal x minus 2. There's my divisor. Okay, that's how I interpret that divisor. And then remember, that's remainder. So this is going to end up being x squared plus x minus 6. And in nice, true Math 30-1 fashion here, this quadratic is typically going to be nicely factorable. Doesn't always work like that, but often it does. And this is going to be x plus 3, x minus 2. Okay, and actually, so I can rewrite this. I could rewrite this as x plus 3 times x minus 2 squared. Would have been an okay way to write that in factor form. Good, that's what we're looking for.
Determine the zeros of the following. X cubed plus 2x squared minus 9x minus 18.
Okay, so now the process of determining the zeros of a function is really just taking it one step beyond factoring. That's all it is, okay? So as soon as you've got it all factored, what we're going to do is set it equal to 0 and identify what the, basically what the x-intercepts are, if you want to think of it like that. So here, first thing we want to do is we need to factor it. So now, are there any common factors here? No. So what we're going to do here is we're going to pull out the little sheet and we're going to look for factoring by grouping. So, yep, this is going to equal, I'm going to group together the first two terms, so x cubed plus 2x squared, big old plus sign in between, and I'll pull that negative in with the 9 and the 18. Sorry, so the negative 9x and the minus 18, I need that together. And so now what I'll do is I'll take out what's common out of those first two, so I'll get x squared, and then x plus 2. Take out the negative 9, and I'll get x plus 2. Now, look at that. That's exactly what I wanted to happen here. There's a common x plus 2 to both of those terms. This x plus 2 has been distributed. Okay, x plus 2 was obviously distributed to an x squared and the minus 9. So now I can factor this right here. Okay, x squared minus 9 jumps out at me as a difference of squares. That's x plus 2 now times x plus 3, x minus 3. Well, this is awesome. Now, if I set this equal to 0, okay, because remember, this is my p of x. This is my p of x all the way down here. P of x, p of x, p of x. If I now set this thing equal to 0, what I can do here is I can solve. I know that this factor would go to 0 if x is equal to negative 2. This factor goes to 0 if x equals negative 3. And this factor here goes to 0 if x is equal to positive 3. So those are the three distinct factors that I've been looking for that would be called the zeros of this particular function. That's it. So in this case, factoring by grouping worked just great.
X to the fourth plus x cubed minus 13x squared minus 25x minus 12.
All right, same thing with this one. What we want to do here is factor this. Now, the first thing I'm going to do is look for common factoring. And I don't see anything. The next thing I would do is look for grouping here, but really there's nothing here. I mean, I'm not going to be able to group this into two separate even groups here, okay, equally sized groups. I'd have to break this into like a polynomial, sorry, a trinomial and a binomial. And really, we're not really going to expect you to do that sort of thing here. So what we're going to expect you to do here is to do some of the factoring using the remainder theorem. Because my constant here is negative 12, my possible roots here, my possible values of x here, x-intercepts or zeros, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And I know that's terrible here. But for this particular question here, I'm going to show you how we get around that. So those are my possibilities here. Now, I'm going to make a guess. In previous questions, when I did this, I guessed and I kept guessing until I found the one I wanted. Now I'm going to be able to guess instantly the one that I need, because what I'm going to do is I'm going to go to the calculator here, okay, and I'm going to enter this in, and I've already entered the equation in, okay, to y1, and I'm going to now go to my table of values. So second table, it's going to show me this list here. We'll zoom in. And what I'm going to do here is I'm looking for the zeros here. I'm just going to pick one. Okay, and let's pick this one. So if x equals negative 1, I get 0 here. So I'm going to test x plus 1, okay, because that's going to tell me to make x equal to negative 1. So p at negative 1. Now I already know that that should equal 0. I'm sorry, you didn't see that here. Let me zoom out a little bit. If I plug negative 1 into this, it's going to be 1 minus 1 minus 13 plus 25 minus 12. Okay, well the 1 and the minus 1 cancel, the negative 13, negative 12, or negative 25 plus 25 is 0. So that does equal 0. There it is. I knew that was going to happen here. So now I'm going to divide. Okay, I'm going to divide by that x plus 1. So I'm going to put the negative 1 outside, and I'll put my coefficients there. 1, 1, negative 13, negative 25, negative 12. And bring down the 1, multiply, add, and I get 0. Multiply, add, negative 13, multiply, add, and I'm going to get negative 12, multiply, positive 12, add, and I get 0. And there we go. Wonderful. So now I will write my division statement here. I'll put my divisor right here, x plus 1, and then this is going to become, well, okay, this is my remainder. So constant, linear, quadratic, cubic. So I'm going to get x cubed minus 13x, okay, because there's a 0 in front of the x squared, minus 12. Now, this is a cubic. This isn't a simple quadratic that I can just work with. So I need to factor now my cubic. I've still got 12 as that final constant there. So I've still got all of these other possibilities here. It could be x is equal to plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. So what I'm going to do is go to my calculator. Okay, now you can do this one of two ways here. All I did with the previous question was take out that x plus 1 factor. So the old equation is still in there, but I can still see that there's a couple of other zeros popping out here. I haven't pulled them out, so they must still be in there. So for example, this one right here, when x is equal to negative 3, so I'm going to test x plus 3 as a factor here. Now that means making x equal to negative 3. So I'm going to put p of negative 3 in there. Now I'm already pretty sure that's going to be a 0 here. But what I'll do is I'll go to my calculator here and I'll enter that in. So what have I got here? I'll put in negative 3 to the 4th power plus negative 3 cubed minus minus 13 times negative 3 squared minus 25 times negative 3 and then minus 12. Oh, and look at that. I got a 0. That's fantastic. So I know that that is a factor. X plus 3 is a factor. So, and it has to be a factor of this cubic right here. It has to be. Okay, because I pulled out x plus 1. I knew there was still an x plus 3 somewhere in there. So I'm going to pull it out of here now by doing my division. So I'll put negative 3 outside. And I'm just going to divide it into this cubic here. My coefficients will be 1, 0, negative 13, negative 12. Okay, I have to have a placeholder for the squared term. Again, the squared term didn't show up. Okay. I already know that this should be 0. But here we go. Bring down the 1. Negative 3 times 1 is going to be negative 3. Add negative 3. Multiply, I get 9. Add, and that should be, what is it, negative 4. Multiply and add, and I get 0. Awesome. So now I know that my polynomial is going to be, now don't forget about the x plus 1. Okay, don't forget about that factor that I found initially. Okay, you still need that. But now I have this additional x plus 3 factor, and that has left me with x squared minus 3x minus 4. Okay, now this one is now just a nice little quadratic. I should be able to factor that pretty handily. What have I got here? That's got to be x, that's got to be x. I want this product here to be negative 4, and I want this to be negative 3. So I'm guessing that one of these has got to be negative 4, and one of these has got to be x plus 1. Okay, let me just double check that. Yeah, and so that's where I'm going to get that negative 3 from in there if I multiply that out here. Now think about this. If I let this now equal 0, then my possible zeros here of this function are going to be negative 1 will make this factor equal to 0. Negative 3 will make this factor equal to 0. Positive 4 will make this factor equal to 0. And I've already dealt with the x plus 1 factor because it shows up twice here. And so right there, those are my 3 zeros of this polynomial. Negative 1, negative 3, and 4. There's a lot going on in this question. Okay, that's a big one here. But now we've got a nice procedure for just systematically working through and pulling out factor at a time until we've got it to a nice little quadratic that we can factor like we've done countless times before.
Algebraically solve the following, expressing all answers in exact form. X to the fourth minus 9x cubed plus 18x squared plus 12x minus 16 equals 0.
All right, so for this one here, I'm going to let you know a little secret. When we say exact form, that is implying something that might exist in this problem. And actually, in this case, it really does here. What this is suggesting is that at some point, you're probably going to have to use the quadratic formula. Okay? Just letting you know that right now, that when you see exact form, that's what it's implying. And at some point, we're going to have to give an answer in the form of, well, we're going to have to use the negative b plus or minus the square root of b squared minus 4ac all over 2a. And we're going to have to reduce that down as much as we can. Okay, with that being said, let's take a quick look at the equation here. Okay, now we're going to take out what's common, and yeah, nothing. Nothing, not seeing it. Nothing common there. Grouping probably isn't going to be a good option here, again, because I'd be grouping into a trinomial and a binomial, and we're really not expecting that kind of grouping to be useful to you right now. So we're going to jump right in and take a look at the integral zero theorem. So my possibilities are going to be plus or minus 1, because remember, I'm looking at the negative 16 now. Plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16. I guess we jump right up to there. Okay, so now I'm going to be lazy. What I'm going to do, and I've already done this, okay, I've gone to the calculator and I've entered in our equation into y equals. So now I'm going to go to my table of values and I'm going to start looking for a 0 here. Now notice when x is equal to negative 1, I get a 0 popping out. Okay, that's a good sign. So x equals to negative 1 means I'm going to test x plus 1, as a factor. And that implies x equals to negative 1. So we'll plug that in. So this will be p at, put x there. I meant to put negative 1 there. P at negative 1. That's going to equal 1 plus 9 plus 18 minus 12 minus 16. Okay, so what do we got here? Minus 12 minus 16, that's minus 28. 1 plus 9 plus 18. Oh, look at that, 28. So those cancel each other out. We're getting 0. So, and I knew that was going to happen there, but it's good to take a look at it and just confirm. So now I'm going to do my synthetic division. I'm going to put the negative 1 out there. I'm going to put the coefficients down here. So 1, negative 9, 18, 12, negative 16. And I already know that my answer here should be 0. Okay, but we're going to walk this thing through. Bring down the 1, multiply, add, multiply, add, what do we got here, 28, multiply negative 28. Okay, and I add here, this is going to be negative 16, multiply and I'll get positive 16, add and I get 0. So there it is, there's my 0. I knew that was supposed to happen, and it did. Perfect. So now my polynomial is going to be x plus 1 multiplied by, well, there's my remainder. So this is going to be constant, linear, quadratic, cubic. So x cubed minus 10x squared plus 28x minus 16. Okay, well, I'm left with a cubic here. Okay, now let's take a quick look at this thing here. Is there anything common to all of those? Well, no. If I did some grouping here, grouping there, would I be able to pull out? See, there'd be nothing that would be left over that would be common. Like, I don't see anything there that would work out nicely. If I took out whatever's common here between 28 and 16, I'm going to end up taking out a 4. That'll be 7x minus 4. Well, there's no way I'm getting a 7 out of that. So common factoring isn't going to work here. Sorry, grouping's not going to work here. I got to go through and apply the same rule here, the factor theorem and the remainder theorem to this. I'm going to apply my integral 0 theorem. And look, I've got negative 16 again, so all of my possible factors are exactly the same. So it's a good thing that I left that previous function in the calculator. So I've already pulled out this negative 1 here. Do I see anything else? And look at that. Down there, when x is equal to 4, I get a 0 here for y as well. So x equal to 4. 4 is an x-intercept. So I'm going to test the x minus 4 factor, which means letting x equal positive 4. So p at 4. Now that should equal 0, but I'm going to go up here and test it again. I'm going to go use the calculator here. Okay. Oops. So there's my function right there. I'm going to plug 4 into that. So 4 to the 4th minus 9 times 4 cubed plus 18 times 4 squared plus 12 times 4 minus 16, and that should be 0. Good. Good. So I know that that does become 0. So now I'm going to do my polynomial long division, or sorry, I'm going to use synthetic division. I'm not going to do long division here. I pull my coefficients out. So 1, negative 10, 28 minus 16. Bring down the 1, multiply, add, multiply, add, multiply, add, and I get 0. And that's exactly what I was expecting to get there, okay? Because I knew that the remainder there was going to be 0. Because I knew it was a factor. So now this tells me that I'm going to get p of x. The original polynomial is, don't forget about that original factor that I pulled out, the x plus 1. So it's going to be x plus 1. Now multiplied by my new divisor here, x minus 4, and now multiplied by the quotient. Now remember, this is the remainder. So I've got constant, linear, quadratic. So x squared minus 6x plus 4. Okay, so now we're still going to try to solve this equation here. Now, and again, solving the equation really is like finding the zeros of this function. So it's exactly what we've been doing. It was exactly what we did in the previous two questions here. So at this point, remember, I'm setting this equal to 0. I'd like to factor this, but I can't. Okay, there are no factors of 4 that I can use, nice integer factors of 4 that I can use to get, a sum here of negative 6. So my answers are going to be negative 1 from this first factor, positive 4 from the second factor here, and now this guy right here, I'm going to have to use the quadratic formula on. So x is going to equal the negative of negative 6, so positive 6, plus or minus the square root of negative 6 squared is going to be 36, minus 4 times 1 times 4. So actually I can do a little bit. That's going to be 16. All over 2 times 1. Now, that is going to equal, okay, and I'm going to come over here, that is going to equal 6 plus or minus the square root of, okay, 36 minus 16 is going to be root 20 all over 2. This is going to be the same as, okay, there's a 4 in there, so I can take out that 2 there, root 5 over 2. Whew! Notice I can distribute this 2 in the denominator of both of those, and I'm going to get 3 plus or minus root 5. Okay, now, therefore, my answer is -1, comma 4. Those two right there. And then this all simplified down into the 2 factors 3 plus or minus root 5. Don't evaluate the decimal here because the question asks for it in exact form. If you try to evaluate the square root of 5 on the calculator, you're going to have to round it. And as soon as you've rounded it, it's no longer exact. Okay? It might look precise. Okay? A lot of times people confuse being exact with being precise. You can have a whole bunch of decimals there, but as soon as you stop writing that decimal, you've had to round it or truncate it, and the answer is no longer exact. This is what they're asking for.